friends, welcome to Brain Amplifier, and in this video we will be discussing about the RMS value, that is root mean square. We'll be discussing what is the root mean square values, why we are calling it so, what is its physical significance. So to start with, first we will find out how we can find out the root mean square value of some waveform. Nothing, it's very easy. Just go from the back side of the name. If you have some waveform, first square that, the mathematical function of that waveform, first square that, then find out the mean of that squared value. The mean is nothing but the average, okay, and then take the root of whole thing. Simple. So first square the values, then find the average of these squared values, and finally find square root of this average. Suppose if I want to see it mathematically, suppose I have some waveform called y. It is the mathematical function of my waveform. So first I have to square this y. So first I have squared this. I'll get the y square. Then I have to find out the mean of this y square. So to find out the mean is nothing but the average. So suppose this is my waveform. Okay, this is point A and this is point B. I have to find out the average from A to B. So average is nothing but summation of all the values divided by number of those values. So if I have to find out summation of this waveform from A to point B, I have to do integration with respect to time from A to B. So I have integrated this y square with respect to time from A to B and divided by the number of values, that is B minus A, that is 1 divided by B minus A. So thus you can find out the RMS value of this y. But again, am I mad why I'm doing all this mathematics? See, suppose if you have some DC, okay, so for that DC you have some fixed value of that voltage or current for that waveform. Okay, suppose this is 5 volt DC, then you have this 5 volt for this waveform. But if you have some alternating waveform, some waveform which is changing its position with respect to time, then you cannot find some absolute value for that waveform. That is, suppose this is my waveform, this is AC waveform, then if I have to indicate this waveform by some fixed value, then it is hard to define, because this waveform has different values at different points of time. Somewhere it is 0, somewhere it is very high, somewhere it is negative. So to find out a fixed value of this waveform is very difficult. Now you can say, why you're not going for the average values? You can always find out the average of a waveform. Yes, you're right. But why we are not going to the average? The reason behind this, we'll see. Suppose this is my waveform, okay, AC waveform. We'll be considering only AC signal because that is the most important part. So suppose I have find out the average of this AC waveform for the half cycle from point A to, suppose this point is t by 2. If the complete cycle is t and the time period is t, then it will be t by 2. So Vp is my maximum value, that is peak value of voltage, and this is sinusoidal waveform. So my waveform is Vt equals to Vp sine omega t. This is the equation of my waveform. So if I want to find out the average value, then I'll have to integrate it from 0 to tau by 2, that is tau by 2 is here, 0 to tau by 2, then Vp sine omega t dt with respect to time, and divided by t by 2. The average value for the half cycle come out to be 2 Vp upon pi. Okay, very good, very good. But if I want to find out the average value for the full cycle from point A to point B, that is, my waveform is Vt equals to Vp sine omega t, and if I find out the value for time t is 0 to tau and divided by tau, the average value comes out to be 0. Now from the experiences, you know that if you're taking some power from your wall socket, it is not giving you 0 power. I mean, it is not giving you 0 voltage or 0 current. You are consuming power because our equipments absorb energy in both positive as well as negative cycles. Even the average value of this waveform is 0, still our bulbs light up, our wires are heat up, maybe in toaster or any equipment, our tungsten based filament bulbs all light up. So everything is working on a zero voltage average. So mathematically this is true, but if you want to find out the inside of this thing, it's very hard to explain it physically. So what is the solution? First we have to understand why I'm getting this average value 0, because I have the negative part of the negative area of this waveform is equal to the positive area of this waveform. That is why I'm getting the 0 average value. Now the solution can be, if I remove this somehow if I can remove this negative part, then I can find the absolute value for this waveform. Because in this waveform it's hard to find out the absolute value because average is coming out to be 0. So if I have to shift this negative part upside, what is the easiest thing? I mean, you're not a dictator, you cannot do anything with whatever you want. You have to put some mathematics. So what mathematics can shift the negative part to positive? You can square it. By squaring, the negative part will become positive. Okay, I can do that. So here is the introduction of root mean square values. So if you want to find, suppose this is my waveform, okay, now you have to find out some absolute value of this. You cannot find the average value because average is coming to be 0. Now first I'll square this waveform. Okay, so after squaring, what will happen? Suppose this amplitude is 2. Okay, for example, this amplitude is 2. The peak will get onto the value 4. Okay, this will be 4. As well as if this part was my -2, the square of this will shift up on the above side and it will also come out to be 4. So now my waveform will look like this. The amplitude will be double, the peak value will be doubled. Okay, now I have a positive waveform. Now if I find out the average of this waveform, it is possible to find a absolute value. So what I do, I find out the average of this squared value. So when I find out the average of this squared value, mathematically what I see, that the average absolute value will come out to be half of this peak value. That is, it suppose this peak value was Vp square, this was my Vp, this was my Vp square, then this average value will be coming out to be Vp square by 2. That we'll see in the mathematics section later on in this video. Vp square by 2. So if this is 4, and it will come out to be 2, that is half of it. Okay, now see, we were not able to do simple averaging. So what we did, we first squared the value and then averaged it. Now I have to remove the effect of this squaring. So what I should do, I should take the root of this thing to undo the effect of this squaring. Okay, so first square it, then find out the average. Now I have to take the root of this average thing to undo the effect of this squaring. So when I will find out the root of this 0.5 factor, it will come out to be 0.707. That is, if I take the root of this, okay, it will come out to be Vp by root 2. That we'll see in the mathematics also. So here we are seeing that the RMS value of some waveform is 1 by root 2 times, that is 0.707 times the peak value. If this was my peak value, my RMS value come out to be somewhere here. It is 0.707 times. So now we are clear that it was very hard for us to find out the absolute value of this waveform. So first you put the reasoning that why not average value. We removed that reasoning by saying that average may come out to be 0 if my positive cycle is equal to my negative cycle. So what we did, we first squared this, then find out the average, and then took the root to undo the effect of the squaring. Now this thing is called root mean square. This was introduced to find out the absolute value of some alternating waveform, because AC was very popular and you have to find out some absolute value, so it became, the RMS value became popular. Now if we will see the mathematics of this RMS value, suppose you have to find out the RMS of some waveform called V with respect to time. So first you have to square it. We have squared the voltage value and we have got the V square. Now we have to find out the mean of it, the average of it. So if for the complete cycle, if my time period is tau, we will find out the mean from 0 to tau, V square t with respect to time, and divide it by tau. And now we have to root it. First we have squared it, then we have find out the mean, and then to undo the effect of this squaring, we have find out the root. So if my value of V is Vp square sine omega t, Vp square sine square omega t, that is the value of V square from 0 to tau, 1 by tau under the root. If you will calculate, do the mathematics, you will find out the value comes out to be under the root Vp square by 2. Now the average comes, if you don't see this root, the average comes out to be half of the squared value that we have seen in the waveform. Okay, and if you will take the root, it will come out to be Vp by root 2. That is RMS value of some waveform is the 1 by root 2 of its peak value, that is 0.707 times peak value. It stands for only the sinusoidal waveform, because the equation we have, the RMS value we have find out, we have put the value of V as sinusoidal. If you have to find out the value, RMS value of some other waveform, maybe triangular, maybe sawtooth, maybe rectangular, then put that equation in this place. Okay, that will come out to be something different. Okay, now you must, if you have read about something RMS, the one sentence always strike, that RMS value is the effective value of a varying voltage or current. It is the equivalent steady DC value giving the same effect. So what does this actually mean? That RMS value of some waveform is equivalent to the DC value. What does this mean is, suppose you have a bulb. Now this bulb must be having 100% resistive component. So if you will give it a 6 volt DC supply, or you give it a 6 volt RMS AC, okay, the bulb will light up equally, it will give same light. You got my point? I mean, if you give it a 6 volt RMS or give it 6 volt DC, these will produce same effect in this bulb, until unless this bulb must be having 100% resistive element. Okay, if somewhere it is written that 6 volt AC, it is understood that this 6 volt is RMS. That is, wherever you read any value of voltage or current in the AC system, it is always RMS value, until unless it is mentioned that it is peak value or average value or something else. By default it is RMS. I mean, if you read 230 volt, it is RMS. If you read 11 kV, it is RMS. If you read some current value 5000 ampere, it is RMS value, because in AC, if you are mentioning some absolute value, it must be RMS. Okay, now if you will give 6 volt peak or 6 volt DC to a bulb, the 6 volt DC will light up more than 6 volt peak, because if peak is 6 volt, the RMS will come out to be 4.2 volt. Okay, now there is one more thing. All the AC meters, be it ammeter, voltmeter, or any kind of meters, they always show the RMS value of voltage or current. Okay, because you have to those meter, the digital meter show some absolute value, so those are configured like they show you the RMS value. If impedance consists of pure resistance, RMS value of AC wave is called the DC equivalent value that we have told earlier. So this is all about the RMS, root mean square value. Hope you have understood it. If you like the video, please hit like, share the video, and subscribe the channel. If you want to keep yourself updated, hit the bell icon on the channel. Thank you so much. So in the end, if I brief the things, the RMS value we introduced because it was hard to find out some absolute value for some alternating waveform. So that's why RMS value was introduced, and it is just a mathematical value that represent the value of some alternating waveform. Thank you.